Then we convert it to nanometers. Okay, so Samantha, do you want me to review this? Did you see what I did? Okay, well, I can't hear you. Uh, Anyway, so that's how you would, this is how you would get the energy of the transition in the hydrogen atom from n equals 3 to n equals 2. You see it's negative, but it's the same number as the photon energy, but photon energies are not negative. It's negative here because it just means it releases energy. Anyway, so then you set this photon energy is what's in this equation, and you can solve for lambda by just flipping these two. You're allowed to do that. It's like dividing each side by e photon and multiplying it by lambda. It works. And then using Planck's constant here, the h and the speed of light, and just dividing by the photon energy and converting it to nanometers. But you wanted to know, how do you, by the way, I want to show you that I did put this on the first page of the exam. So you'll be able to tell the order of the orbitals, okay? All right. So if you're just given a frequency or like, suppose I tell you a photon has a frequency of 4.16 times 10 to the 16th hertz or inverse seconds. What is the wavelength? Then you would just use lambda as c over nu. Just made that up, so I don't really know where that is, but that's okay. Okay. Did that answer that question or not? Anybody have another question? Am I muting all of you because I can't hear a thing? Huh,
No, I can hear you and speak all right.
okay. Everyone's just not
It did
talking.
help, thank you.
Okay.
I haven't really gotten to do enough to have any specific questions.
Yeah,
Just hoping to take down some notes and review it. You will be hosting another one like tomorrow night, I think, right?
yeah, tomorrow night. Yeah, for sure. Well, it's hard to run these things if people don't ask questions.
Let me look through the study guide and see if there are any that look particularly annoying.
We could practice doing some Lewis structures because we haven't, you need to practice that. That's a significant portion. Lewis structures and formal charges. In fact, maybe we should get that from the handout. Let me take a look.
Doesn't sound like a bad idea.
Yeah. Okay, so this is from the end of the handout of the review. This is from the review. So do you want to try writing them yourself? So remember the rules we use here, right? We count valence electrons. That's the first thing you do. What's the second thing you do?
Electronegativity.
Right, you figure out which element or which atom is in the middle. And except for, it's never hydrogen. Hydrogen is always on the outside, but it's usually the lowest, the atom with the lowest electronegativity usually is put in the center because it has to share electrons with lots of different atoms, and electronegative atoms don't really like to do that because they're very electron grabby. Then what do? You also divide by 2 for the number of pairs. It's pairs, not Paris. Now I'm writing Paris. Okay, then what's the thing you do next? If once you have that, then you have the skeletal structure. That's like this, the order of the atoms that leads to the skeletal. That's what I call it, structure. After that, what's the first thing you do? Place what?
Place all of the atoms with single bonds.
Right, you place single bonds between the atoms. Okay, then you have some pairs left over. Place the leftover pairs as lone pairs on the outer atoms first. If there's any leftover ones that haven't been used, place on the center atom. And by the way, you would never, it says to place lone pairs as lone pairs on the outer atoms first, but never on hydrogen. Hydrogen can only have one bond to it. Okay, so you would never place those leftover lone pairs on hydrogen. That wouldn't make sense. Okay, so count the valence electrons, draw by 2, get the pairs, figure out which atom is in the middle. Usually it's the one with the lowest electronegativity. Place single bonds between atoms. Place leftover pairs as lone pairs. It's hard to read. On the outer atoms first, but never on hydrogen, because hydrogen can only take one bond, only has room for 2 electrons. Any leftover pairs, this means, place on the center atom. And now, then is when you review the structure. And what are you looking for when you review the structure?
To see if the total amount of pairs aligns with what it's supposed to be.
Well, that's true. You want to see that you have the correct number of pairs. That's true.
And if you end up with more pairs than you're supposed
But
to
that's
swap
not
out some.
really. I mean, sure, you want to make sure you count it right. But the main thing, the most important thing is to see if you have octets. That's 8 electrons on the atoms that aren't hydrogen, right? Okay, so let's go ahead. Do this one, this SO2. So how many electrons there? And come on, some of you, I mean, need to participate here. This isn't just Paul answering all the questions. How do you figure out the number of valence electrons for sulfur? What do you look for? Presumably you have your periodic table, right? So what are you looking for? Maybe I muted all of you. Let me see. I don't know. You all muted yourselves.
I'm trying to catch up in the notes is all. I'm fiddling through my papers.
I know you just got here. Oh, well. It just doesn't make sense for me to answer all my own questions. It's like sort of purposeless.
Well, we need to count up the valence electrons first.
Yeah, so how do you figure out how many valence electrons sulfur has?
It's based on what period they're in, right?
No, it's what group they're in.
Group.
You look for the group number.
I know it's the horizontal part or the
Actually, the vertical.
Yeah.
Yeah.
I
So for
know, I just
example,
can't describe it.
group 6 is oxygen, and under oxygen is sulfur. It's really 6A or 16. Okay, but it's the 6 that's important here because they all have 6 valence electrons. So sulfur has 6, oxygen has 6 each. So that's 18 electrons. That's 9 pairs. Okay, now which one is going to be in the middle? Is it going to be like this? Is it going to be like this? Which one?
It's the lowest electronegativity, right?
That's right.
Yeah, so sulfur in the middle.
Sulfur would be in the middle. And I'm going to give you the electronegativity chart. So the first thing you'll do, besides putting the sulfur in the middle and the 2 O's, is you'll put 2 single bonds just like that. Then what do you do? Okay, so that uses up 2 of the 9 pairs. You have 7 pairs left. Where are you going to put the 7 pairs? You look at the directions, it says place leftover pairs as lone pairs on the outer atoms first. So 1, 2, I've used up 2 pairs, 3, 4, 5, 6, 7, 8. And now any leftover pairs, you put them in the middle. There's 9. So is this Lewis structure completed?
No, sulfur needs an octet.
Yeah, so there's no octet here on sulfur. You only have 2, 4, 6 electrons. So that's when you make a double bond. The only time you make a double bond is when you need to, because you don't have an octet. So you'll take one of these pairs and you'll bring it over. And so now you could see that you have 2, 4, 6, 8. And then you have 2, 4, 6, 8. Each bond is 2, right? Then you have 2, 4, 6, 8. So we have octets on everything. And also, just to check, you should check to see if you have the right number of electrons. So this is 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 electrons. Perfect. That's exactly what you want. Of course, now I'm trying to erase things and it's getting, so I'm just going to rewrite it. We're not quite done yet though, right? Because there are 2 equivalent resonance forms. And I could have taken and put the double bond on the right. Instead of the left, and still had nice octets with the right number of electrons. And you can see these are called resonance forms. And they happen to be equivalent because they're really the same. Well, you could get the same thing from this one by just flipping it. But anyway, there are 2 equivalent forms, and it's true that in this molecule, the bonding is the same. Now, sulfur, though, is a complicated one because you can do this expanded valence thing. Let's go down here and calculate the formal charge. So this is what we have. So how do we calculate the formal charge on the O here? So in class, I showed you that you could count up the number of electrons. Oh, geez, I didn't do that. Associated with a particular atom. So let's make a little chart. We'll put the valence electrons here. And valence electrons for oxygen. This is the first oxygen. This is the second oxygen. Is 6. And now we're going to count up the actual electrons associated with that oxygen. And so to do that, we would count all the lone pairs, 2, 4, 6, and we would divide the bonds in half. So that would be 7. Then we would take the valence minus the actual. That gives us 6 minus 7. -1. So why does it have a negative formal charge there? Well, it's because the oxygen normally has 7 valence electrons, and now in the molecule, it actually has, sorry, it normally has 6, but now it has 7 in the molecule. So it's got 1 more than what it would have as just the atom. So that's how we calculate the formal charge. Let me get rid of this crazy line here. Make these dots a little more reasonable. All right, now let's do the sulfur, okay? So sulfur is also in group 6. So what's its valence electrons? How many?
Also 6.
Yep. And now if you count, you have half of each of these. So 1, 2, 3, 4, 5. So 6 minus 5 is +1. So the sulfur has a formal charge of +1. And finally, the second O, how many electrons associated with that one? We have these 2 and these 2, that's 4. And then 1 from this bond and 1 from that bond, that's 6. Oh, that's 6 actual, but it also has 6 valence. And so that's a formal charge of 0. Which makes sense, right? Because when you add these up, you get 0, and SO2 doesn't have a charge. It's a neutral molecule. But sulfur, yeah, can also, Yeah, so I think that's all we got here, actually. I don't think you can do expanded valence here. Can you? Yeah, you can. You could do this. So sulfur is in period 3. So don't, in fact, maybe I won't even show you this because I don't want you to do this for other atoms, but sulfur is one of those atoms that can accommodate expanded valence. Because if you notice, it's in the 3rd period. You
Hmm.
you can't do this with any of the elements in the 2nd period that we commonly use, but I could take one of these and make a double bond here, and I would end up with this structure. And this would give everything a formal charge of 0. All the atoms, there are 6 electrons for each one, 1, 2, 3, 4, and half of these. So that would be 6 minus 6, or 0. This would be 0. This would be 0. So this is a better Lewis structure, but it is an exception because we have a sulfur here. If we did ozone, let's try that one, O3. O3 is very similar to SO2 because they're all in period and all in group 6. So how many electrons would there be in O3? How many valence electrons?
Also, how is expanded valence different from normal valence?
Well, that's just what they call it when because you could notice that now in this model here, you have 2, 4, 6, 8, 10 electrons on the sulfur, right? Usually we go for an octet. Expand
Oh, right. I see.
above
Yeah,
8.
yeah,
Yeah.
yeah.
Hold on.
I didn't realize it was holding 10. Never mind. No, I get it.
Yeah, it's okay. I gotta get some water. I'll be right back in a minute, okay? Where am I? Yeah, I'll be right back in a minute. Thing is so obnoxious. Wow, there's a lot of people coming in. All right, right back. Okay. So this is, was an exceptional case, right? Because it has a sulfur and you could have more than an octet.
So for the exam, would all of these technically be correct answers? Or would you not want us to do the expanded valence if it wasn't suggested that we should?
Oh, no. I mean, if you did that, it would be right, but don't do it for ozone. You know what I'm saying?
Hmm.
It's wrong. That's why I'm going to do O3 because O3 also has 6 times 3 or 18 electrons, 9 pairs. There's no argument about what goes in the middle because there's only one type of atom. 2 is used up, so 3, 4, 5, 6, 7, 8, 9. So now we would take one and make a double bond. Okay. And we would have 2 resonance forms. Because we could have made that double bond on the right instead of the left. But that's it. There's no, you can't take and do what we did here for sulfur. because sulfur can't have expanded valence. I mean, oxygen can, sulfur can, but oxygen can't, because this is only in the second period. So what would the formal charge be on this atom? So you can, in your head, divide those bonds in half. So you get 1 electron from each one. 2, this is 1, 2, then you have 3, 4, 5, 6. Valence minus actual. 6 minus 6 equals 0. That's the formal charge on that first oxygen. This one, we have 1 electron, half of this thing. So that's 3, 4, 5. So it's 6 minus 5. Did I do that right? Yeah. Yeah. So that's +1. And then here we have valence minus actual. The actual is 2, 4, 6, and half of this. So that's 7. 6 minus 7 is -1. Right? So it's very much, remember when we first did the SO2, that's what we had. We had a +1 on the central, just the way we have a +1 on the central oxygen here. -1 on the one that has a single bond, and 0 on the one that has the oxygen that has the double bond, just like, see, it's really identical because sulfur and oxygen both have 6 valence electrons. They're in the same group. But here I can't do the expanded valence. I have to keep it like this. Anyway, this is a mess. Okay. So the formal charges would be here, be 0, +1, and -1. But of course, then you have your other form where you would basically have -1, 0, and +1. Oh, sorry, -1, +1, and 0. So the outer oxygens would have some negative charge and the inner oxygen would have some slight positive charge. Anyway. And there's no getting around it because you can't have expanded valence there. All right, let's do another one. Questions about that?
No, that was good.
Okay, good. Let's look at, how about CO? How many valence electrons on carbon? What group is it in?
I mean, I can keep answering, but give somebody else a chance if they want.
All right, whatever. It's 4, and 6 is 10. So that's 5 pairs. So we have CO, we start with 1 bond. Now what do I do? Come on, there's a few of you that could answer this. You put lone pairs on the outer ones, right?
Yes.
So 1, 2, 3, 4, 5, 6. Oh, 5, sorry, I made too many. Okay, so that's no good for the carbon, right? Because it doesn't have an octet. So we'll have to make a double bond. Then we get this. Are we done yet?
Nope.
Because we need to make another one because we still don't have an octet on the carbon. But after we do that, and now we have a triple bond. Let's count up the pairs again. We have 1, 2, 3, 4, 5. So the pairs are all correct, right? You said we had 5, okay. And we have octets on each of these atoms. 2, 4, 6 for the triple bond, and 8, right? So 2, 4, 6, 8 for each one. And so this is the Lewis structure. Just out of curiosity, what is the formal charge on the carbon here? All right, someone tell me, because I don't want to keep doing this myself. I know how to do this already. So how do I count up the electrons belonging to that carbon? How many?
So you count 2 for the lone pair and then 1 for each bond because the bond's electrons are shared evenly.
That's
So
what you
that
do,
means
yeah.
it's 5 actual
That's right.
compared to
So,
the 4 valence.
so this is valence minus actual. Valence is 4. Actual is 5. So that's -1. Here, valence minus actual. Actual is again 1, 2, 3, 4, 5. But it's 6 minus 5. Which is +1. And there's really nothing you can do about it. And notice those charges add up to 0. Which they should, because carbon monoxide is a neutral molecule. Is the CO bond polar? Now, how do you figure that out? What do you need to do that?
The electronegativity numbers.
Yeah. Here it is. Somewhere. What's not there? Here it is. Okay. So carbon is 2.5. O is 3.5, right? So the delta En is 3.5 minus 2.5. So that's for O minus, doesn't matter. You always subtract the smaller one from the larger one. And that's 1.0. Okay. And if you, let's see if I can grab this thing here. This is from another handout I'm getting. This I took from the book, but I changed the numbers a little bit. Right, so this is the table from the book. However, the book has a slightly different criteria than what I use. So I say to be polar, it has to be greater than or equal to 0.5, and it can't be above 1.8, but I didn't really talk about that too much in class because I didn't talk too much about ionic compounds. But anyway, so you could see that difference there, that difference in electronegativity. Where is it? What happened to it? Yeah, so this is greater than 0.5. I should say it's 0.5 or greater. So that means it's polar. The CO bond is polar. Okay. We don't have room to do N2F2 over there, so let's do it down here. Okay, so N2F2. So it doesn't tell you, but if I put this, yeah, N2F2, if this were on an exam, I would tell you that the two N's are in the middle and each one has a fluorine. So that would be your skeletal structure. Okay. So, all right, so what do you think? What do we do? How many valence electrons? How many pairs? How do we deal with this one? What's the valence of nitrogen?
5.
So what's the valence electrons for fluorine?
Seven.
It's in group 7, so it's 7. So that's 7, 14 plus 10 is 24. That's 12 pairs. Okay, maybe it's 14. Yep. Okay, so you start by putting your single bonds. You use up 3 of them. Okay. So that's 3, 4, 5. Notice I'm on the
Yeah.
outer electron. 6, 7.
Fluorine is more electronegative, so shouldn't it go in the center and not on the ends?
The less electronegative goes in the center.
Oh,
Yeah.
also, how do you tell when exactly to put it into a line? Is it because
Oh, I could have done it
opposed-
this way. I could have done it this way.
Does it matter which way you want us to do it on the exam?
Okay, here it is. For this exam, we haven't yet learned geometry. That's what we're in the process of learning for the final. So on the final, I could ask you to, well, when you draw the Lewis structure, you could draw it either way. But then when you go to figure out the geometry, you have to draw it in the way that it is. Okay. You get what I'm saying?
The plot thickens.
Yeah. It's true. So what were we up to here? We had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now I'm working with the leftovers, right? 12. Okay, so I've just used up my electrons. Right, something went wrong here. All right. I have 1, 2, 3. Then I have 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, what's the problem here? There is a problem.
The second nitrogen.
Yeah, the second nitrogen does not have an octet. So I'll make double. Wait. No, wait a minute. That's not, no, that's what I'm gonna do. Yeah, I guess I would do this one first. Question is why? I guess you could have a legal form that way too, but I bet it's gonna have worse formal charges. Anyway, let's see what we got here. We can investigate that later. Okay, so now let's just make sure we have the right number of pairs. We have 3 on this one, 4 for the single bond. Just count up the pairs. I can't really show you how to do it. I'm making too many marks when I do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, it looks like it's not. Wait, 1, 2, 3, 5. Oh, I'm
Just the double bond.
oh yeah, I forgot the double bond. Good. All right. Yeah. So that's a legal Lewis structure that gives everything an octet, but it's very interesting because I almost did it the other way, right? What if I was at this stage? Okay, now what if I did this? And then I ended up with this structure. Yeah. This is not, okay, so now what would be the formal charge on the fluorine in this case? Let's do the formal charges on all of these. Okay, remember what we're doing. We're going to do the valence minus the actual. So what's the actual for fluorine? Oh, yeah. before we move the electrons over, like when it's like that. 1, 2, 3, 4, 5, 6, 7, right? Because you're dividing this in half. But fluorine has 7 valence. So that would give it a formal charge of 0. Nitrogen, 1, 2, 3, 4. This would be +1 because it would be valence minus actual would be 5 minus 4. Am I right? Check me because I'm not doing this with any notes. This is +1, okay? Here, this nitrogen, how many electrons on the nitrogen? Well, 1, 2, 3, 4 from lone pairs, and half of each of these bonds, that's 5, 6. Valence minus actual is 5 minus 6, or -1. And finally, this fluorine, 1, 2, 3, 4, 5, 6, 7 for actual, and 7 for valence, so that's 0. So look at that. We have a -1 and a +1. Okay. I forgot the double bond, didn't I? Damn it.
Yeah, I was gonna
That
say,
wasn't
I'm pretty
right.
sure that
Why don't you
form
stop
doesn't
me?
work.
I mean, really.
You're on
I
a
would have
roll.
stopped you earlier, but I only just noticed myself. I was doing that on my own.
Of course. Stopped sharing because it got so upset with me erasing like that, like heaven forbid I could erase like that.
Not forgiving on a Sunday night.
What is doing? I'm just gonna have 3 versions of these open now. Yep, that's what it's doing. Okay, I got one, but I think I have to share again. All right, stop me, stop, you should have stopped me, but it's my fault. All right, so this was a double bond. And this wasn't here. Right? Yeah. Yeah, I didn't think that was right. Okay, 1, 2, 3. Wait a minute. It's a double bond. Okay. All right, so this nitrogen is 1, 2, 3, 4, 5. So valence minus actual is 5 minus 5, or 0. And the same thing here. And this formal charge, this fluorine is 3 lone pairs and 1 bond. So that's 7 electrons. So valence minus actual is 7 minus 7, or 0. So this structure here with the double bond between the 2 nitrogens gives formal charges of 0 to all of the atoms, which is desirable. That's good. That's much better than what we're going to get down here. Now down here, you could see that we have 1, 2, 3, 4, and half of these bonds, 5, 6. So that's the actual. Actual is 6, valence is 7. So that is a fluorine with a +1 charge. What do we know about fluorine on the periodic table? Remember what's happening to electronegativity on the periodic table. Fluorine is the most electronegative element on the periodic table. It does not want a +1 charge. Okay, so it's much better. This is a much better structure right here. The one that puts the double bond between the nitrogens, with each fluorine having 3 lone pairs. Much better. So anyway, that's a formal charge of +1. This nitrogen has 1, 2, 3, 4, 5. It's 0 because its valence is 5. And I just counted up 5 electrons associated with it now. So it's 5 minus 5. This one is going to be 6. 1, 2 from each bond, and then 3, 4, 5, 6. So this is valence minus actual is 5 minus 6, or -1. And this one is actually got a formal charge of 0. So we have a -1 here. We have a 0 here. So you see now we have, you know, a -1 on N and a +1 on F. But fluorine doesn't accommodate a positive charge very well, even though nitrogen is sort of okay, maybe with a negative charge because it's somewhat electronegative. But fluorine with a positive charge is not going to be good. Oh, by the way, these are not dots here. These are zeros showing the formal charge. They look a little like electrons, but that's not what they are, the formal charges. So this is the one that gives everything a formal charge of 0. And so that would be the best Lewis structure. Okay.
Mhm.
Let's go back. We did this one, yay. Is the NF bond polar? So if you look up on the electronegativity chart, here's N, 3.0. Fluorine is 4.0. The difference is 1. And so it's 0.5 or greater. So yes, it would definitely be a polar bond. Okay, let's go down here and do H2CO. Carbon has the lowest electronegativity compared to oxygen. Hydrogen is never in the middle. It can be in the middle. Let's count up the valence electrons. We have 2 plus 4 for carbon and 6 for oxygen. That's 12. That's 6 pairs. What do we do first?
Bonds to the outer atoms.
3, 4, 5, 6. What now? Need to get an octet on this carbon here, so I have to make a double bond. And after I do that, that's the Lewis structure. Now, getting back to what you were asking me about how to draw that, what we're going to learn really on Tuesday is that when you have 3 groups of electrons on the central atom, and a double bond counts as 1 group, they will try to get as far away from each other as possible. That will mean that they will end up like this, with 120-degree angles in between them. That's how I know that this is the correct way to draw this in terms of the geometry. Right, so if we go back to, but that's not going to be on the test because we didn't get to that yet. But if we look at this molecule here, you see there's 1, 2, 3 groups of electrons on each nitrogen. So what you will have is a 120-degree angle. So this is 120, 120. These are all 120-degree angles. Anyway, but that's for another day. All right. Okay, H2CO, just getting back to the formal charge. Is anything funny going on here? What's the formal charge on this carbon?
0.
Yep. The valence is 4. The actual is half of each of these bonds. So you get 1 electron from each of these, 1 electron from this, 1 electron from that. That's 4. So 4 minus 4 is 0. So the picture is ugly and messed up, but you have a formal charge of 0 on that carbon. Formal charge on hydrogen is just about always 1. Sorry, 0, not 1, as 1 electron. And the valence is 1, and it has half of 1 bond, which is 1, so the formal charge is 0, 0. Oxygen, we have 1, 2, 3, 4. What did I do here? Oh, I have an extra lone pair here. I copied it wrong. See, someone could have got a gotcha there. 2, 4, and then 1 of each of these. That's 6. Valence minus actual is 6 minus 6, or 0. Now is the time to ask if you don't understand how I'm doing this formal charge calculation. Because you're going to have to do it on your own without me at some point. Okay. What else is on that? Let's see. Um, Try this one. Okay. So
I think the one thing I wanted to ask you about was with the transitions with photons and stuff,
Yeah.
drawing that little chart with the arrows.
Oh, you mean the diagram, the energy level diagram?
Yeah, it's messing with my head.
Why?
I can't get the arrows to make sense, and maybe it's just I'm overthinking things because that's what
Probably.
happens.
Okay, here's the thing. You draw these as lines, going up. These are terrible lines, but I'm doing the best I can. So notice that the lines get closer together. This is the first energy for n equals 1. Then we have the n equals 2. They get closer and closer together as you get higher. It's because of the n squared in the denominator, but then we have E3, E4, and let's just stop at n equals 5, okay? So I suppose you have a transition from n equals 4 to n equals 1. Okay, so that just means you're going from this level here to this level here. So you just draw an arrow.
And that's a higher energy to a lower energy.
Yes,
correct?
energy is increasing this way. These energies are all negative, by the way. They're getting less and less negative as you go up. They're getting closer to 0.
Okay.
If you have a transition from n equals 2 to n equals 4, now this transition here is an emission. let me draw it in black because I'm talking about it in black here. For the red one here, this is an absorption. It's absorbing energy, so it would be going this way. Okay,
Absorption is going from lower to higher.
yeah, so this would have a delta E that's positive, right? This guy would have a delta E that's negative because energy is released.
Right, right.
And here it's because energy is absorbed. Yeah,
Thank you for that.
you're welcome. Okay. Did I copy something? I thought I might have. But... Oh, here, the CNO one. So how would you start going about this? We have CNO. And we have how many valence electrons?
4, 5, and 6.
That's right. So that's, oh, sorry, but it's an ion. Plus
Oh.
1 because it has an extra negative charge. I knew something was wrong because I was getting an odd number, right? 4 plus 5 plus 6 is 15. You can't divide that by 2. So I thought, and then I realized we forgot the negative charge here. Okay. So it's 16. So that's 8 pairs. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, how can we make this molecule work? What can we do here? There's different ways that we could make an octet on the central end. Give me one way that you could do it.
You can take a lone pair from each, the carbon and the oxygen, and double bond the nitrogen.
So we'd have N double bond O. Ooh, that would be a carbon. Do we have octets on everything now? By the way, we have to put a bracket and a negative charge. So this is one possibility, but I tell you here that there are 3 different ones. So what if we didn't do that? What else could we do to get an octet on the middle nitrogen?
Could triple bond something.
Okay, let's take one from here and one from here. And we could have N triple bond. Oh, we only have 1 lone pair left. We have octets on everything. So this is a resonance structure, another one. And what's the other thing we could do? Instead of doing this on the right, we could do it on the left, right?
Mhm.
All right. Now, if I were to ask you, are these equivalent resonance structures? What would the answer to that question be? Remember what an equivalent resonance structure is. So when we have like what we had before with the ozone, These are equivalent. In a sense that, you know, you have one double bond and one single bond. This structure is exactly the same as this one, it's just sort of flipped the other way. But that's not the case with these three, right? Here you have two double bonds here. Here you have a single onto the carbon and a triple to the oxygen. Here you have a triple to the carbon and a single to the oxygen. So these are not equivalent. So how do you tell which is best? The way that we do this is we calculate the formal charges on all the atoms. Okay, and we know that the best thing is to have as few formal charges as possible. And if we have to have a negative formal charge, which you see, because we have a negative charge on the ion, that's going to mean that the charges, all the formal charges, have to add up to -1. Okay, so we're going to have a negative charge on something. All right, I'm going to erase this because it's not really relevant anymore. Nice that it worked. Okay, so we've been calculating some formal charges. We've been using the valence minus actual. Valence, what's the valence for carbon? You look in the periodic table, you see it has a little 4a above that group, so you know its valence is 4. So we have to figure out the actual electrons. So how many electrons are associated with this carbon? Both lone pairs and half of the bonds.
6.
6. 4 minus 6 is -2. Okay. What about this one? Valence minus actual. What is the valence for nitrogen?
5,
What's the actual?
4,
So that's +1. And here on oxygen, what the valence is 6. What's the actual? 1, 2, 3, 4. Half of each of those is 5, 6. That's 0. So if I was going to write this with its formal charges, it would be -2 + 1 and 0. Now, what does this tell you when you look at a thing like this? -2 on a carbon. Carbon is not very electronegative. And having a negative charge of 2 on a carbon is pretty extreme. Meanwhile, nitrogen is fairly electronegative. It does not want to have a plus charge. So I would say this is pretty unstable. By the way, I have to put a bracket, the negative. You'll notice that -2 + 1 is -1, so that's good, but that's nothing new. That's nothing that we didn't expect, okay? So let's go ahead and do the formal charges on these other ones. Let's do it on, what's the, oh, hold on. Oh yeah, this one's even worse. Look at this. What is the V minus A here? What's the V? Valence, 4. What's the actual?
7.
Yeah, so that is a -3 formal charge. Whoa, that is really extreme. Okay, nitrogen. Valence minus actual.
Same thing, 4, 5 minus 4.
5 minus 4 is +1. And this one? Valence is 6 minus 5. This is +1. And notice -3 + 1 + 1 is -1. So that's a sort of a check. And so far it's okay. All right, so we have C N O minus, and it's minus, I want a different color. -3 +1 +1. Oof. Okay. And now this one, the V minus A. Valence is 4, actual is. Let's see, what?
5, right?
5, yep. Equals -1. And then nitrogen here. 4, that's the actual. 5 minus 4 is +1. And this one, valence minus actual, is 6 minus 7. So that one is shut. Okay, and notice they all add up to -1 as well. And these are all resonance forms. Now, which is the best one? Oof. What do they have in common? I think we made a mistake somewhere. I made a mistake, maybe. No, I didn't.
Would you be looking for the most stable one? Is that how you know?
Yeah, I don't think any of these are particularly stable. None of them would be very stable. There's none. They all have formal charges on at least 2, and this has a -2 formal charge. So none of these are great. But look at this, -3. I mean, that's insane, right? One thing you notice is that all of them have formal charge of +1 on the central nitrogen. So, you know, you can kind of rule that out as even being a factor because it's there for all of them.
So that doesn't automatically make it unstable, even though nitrogen wouldn't want a positive charge.
Well, I think probably this is very unstable.
Yeah, so they'd all be
I mean, that's what
unstable.
so
It's
the
just-
overall conclusion here is this does not look like a very stable ion. Okay. But which is the worst? Well, okay, you don't want to have a positive charge on an oxygen and a negative charge on a -3 on a carbon. So I would say this is the worst. This one here that I can't seem to write on. Okay, that's the worst. And this one has a -2 charge on carbon. No, it would be better to put a -1 on oxygen and leave a -1 on carbon. So I would say the third one here is the best. Let's see if I agree with what I wrote on the answers here. Yeah, except I think this was structure 2 on the solution. Yeah, this one I would say is the best. Because, you know, here you have all the negative formal charge, -2 on carbon. That's terrible. Because carbon is not very electronegative. Here, at least you're giving oxygen a negative, you know, half of that burden, and carbon's only having half of it. So I would say that is the best structure, but none are great. They all,
You might be looking for something that's got a balance of the charge. And
it's
that way,
not so much a balance of the charge. No, it's not like symmetry. That's not what it is. It's where the charge is, right? I mean, if in balancing your charge, you're putting, you know, a -2 on carbon and oxygen because there makes it look nice, and that's not going to help you. It's because on the one on the left here, you're putting a -2 formal charge on an atom that's not very electronegative.
okay.
And 0 on one that can accommodate some negative charge. Here, you're sort of splitting it.
Okay. Yeah. So you have to take the electronegativity into account. when you're deciding. Yeah, okay.
Mhm. Anyway, you know, you run out of examples of these things, which is why I'm giving you, you know, this example, because I mean, you know, one of them's in the review, one's on the test, one's in the problems I've done in class. I mean, you know, I'm ripping my hair out trying to think of other ions to give you. Okay, so anyway, that's fine. All right, I think I'm done. I'll see you tomorrow night then. Unless you have a
Thank you.
burning question still to ask.
This is very helpful. Hopefully we'll have more questions. I'll see if I can attend the next one.
Yeah, good. All right, looking forward to it.
Yeah, thank you very much.
Oh, you're welcome. Bye-bye.
Thank you.
Have a good night. I hope you enjoyed your Thanksgiving, Professor.
Oh, it was great. Yeah, I did very much. Bye-bye.